A very warm welcome to the 7th lecture on the subject of wavelets and multirate digital signal processing. Recall that we had ended the previous lecture by hinting at the structure of the synthesis filter bank corresponding to the Haar multi-resolution analysis. Today, we begin by looking at both the analysis side and the synthesis side once again. I mean the analysis filter bank and the synthesis filter bank in the Haar multi-resolution analysis. So, let us put down the two filter banks clearly. You will recall that on the analysis side, we had a structure like this. We had the sequence, let us call it x of n, corresponding to the function in V1. Essentially, it was subjected to the action of two filters, a filter of the form half 1 plus Z inverse another one of the form half 1 minus Z inverse followed by a downsampling by 2. We had also derived the structure of the synthesis filter bank, and interestingly we saw the structure was very similar. In fact, it looked almost like a mirror image here. Except for the fact that you had an upsampler instead of a downsampler, followed by the two filters once again. So, here the filters had the form 1 plus Z inverse and 1 minus Z inverse. Now, the only catch is I am going to allow for an ambiguity of sign here, plus minus 1 minus Z inverse. A small variation from last time, a subtle point, but important. Now, there are several things to which we must pay attention. One is, if you look at the structure of the analysis and the synthesis filter banks, the filters are almost identical. These are the two filters for the analysis side and these are the two filters for the synthesis side. Please note, I am allowing an ambiguity here. What would the physical meaning of the ambiguity be? It would just determine where I place the sum sample and the difference sample. With a plus sign, the sum sample will get placed at the even locations and the difference sample at the odd locations. With a minus sign, it would be the other way around. So, let us leave that ambiguity for the moment. If we try and resolve the ambiguity right away, we might actually get more confused. So, allowing that little ambiguity for the moment, let us analyze this whole structure in general and then resolve the ambiguity. Anyway, coming back to the filter bank structure as we see it, one very beautiful thing that we notice about the Haar filter bank is that the filters on the analysis side and the synthesis side are almost the same, except for this sign ambiguity. And if we really look at it, these two filters are also very meaningful in another domain, of which we shall soon have more information. Now, what we are going to do from here onwards is to look at this general structure. You see, we want to understand why the Haar multi-resolution analysis, though attractive, is not adequate. I have been saying all the while that if we understand the Haar multi-resolution analysis and if we understand the filter bank corresponding to the Haar multi-resolution analysis, we understand quite a great deal about filter banks and multi-resolution analysis. Most of the concepts are captured. Then why should we look for other multi-resolution analysis? That is a subtle point, which we shall see by going into another domain now. So, our objective here is to look at the frequency domain behavior. And how would we get a frequency domain representation of the Haar filter bank? So, what we will do is we will progress as follows. First, we shall look at the frequency domain for the filter bank. And how would we do that? We would do that by substituting z equal to e raised to the power j omega. Let me once again recapitulate a few concepts from discrete time signal processing for the benefit of the class. Although one would have done these in a course on discrete time signal processing, it helps to put some of this discussion in perspective. You will recall that we had defined the Z transform last time. We had said that if you have a sequence x of n, its Z transform is capital X of Z defined by summation n running from minus to plus infinity x of n z raised to the power minus n with Z belonging to a region of convergence. Now, in particular, if the region, so let this region be script R. In particular, if this region includes the unit circle. So, let me say a little bit about the regions of convergence of a typical Z transform. Typically, R has the following patterns. R is between two circles centered at the origin. So, it has an appearance something like this, and both of these are centered at the origin. So, you have R 2 and R 1. So, here the radius is R 1 I mean, and here the radius is R 2. Now, it could be true that R 2 might be infinity or R 1 might be 0. So, we have to allow these possibilities. Most generally, R1 could be 0, R2 could be infinity. Moreover, the boundaries may or may not be included. The boundary circles may be included or excluded. In fact, if these values R1 and R2 are non-zero and finite, most of the time the boundaries are excluded. It is only when R2 becomes infinity or when R1 becomes 0 that there is a question. Is the boundary included or excluded? And that is not a trivial issue. Whether the boundary is included or excluded makes a difference to the properties of the system. Well, all this essentially to recall a few points about the Z transform, and now coming to the frequency domain. So, in particular, if the unit circle, that is mod z equal to 1, it is a circle, you see, mod z equal to 1 is a circle of radius 1 in the z plane. So, if the unit circle is included in R, then we have a frequency response for the system. The system has a frequency response. That is, you see, we talk about the system having a frequency response if the underlying Z transform is a system function. If the underlying Z transform is a system function. And of course, otherwise, in case we are talking about a sequence, then we say the sequence has a discrete time Fourier transform. So, if we are talking about the Z transform of a sequence, we say the sequence has a discrete time Fourier transform. This is an important concept, a DTFT for short. Either way, what we are saying is, in case the unit circle is included in the region of convergence, then we have an even more interesting interpretation of the system function or the sequence in question. And in fact, if we look at all these Z transforms encountered in the Haar filter bank, they all satisfy this. So, we are now entitled, or we are now well poised to look at the Haar filter bank in the frequency domain. And what do we mean by the frequency domain? With mod z equal to 1 or z equal to e raised to the power j omega. Indeed, Consider the analysis side, the analysis filters. Both of them have a frequency response, obviously. Let us take the filter 1 plus Z inverse by 2 and let us look at its frequency response. Of course, we would obtain the frequency response by substituting Z equal to e raised to the power j omega. And that would give us 1 plus e raised to the power j omega by 2 minus j omega by 2 if you like. Which we can simplify. We can take an e raised to the power minus j omega by 2 common here and then put e raised to the power j omega by 2 plus e raised to the power minus j omega by 2 inside the bracket and leave the half factor as it is. So, this is what we have here. Now, recognize that this is essentially 2 times cos omega by 2. And therefore, we have half e raised to the power minus j omega by 2 times cos omega by 2, which gives us e raised to the power minus j omega by 2 times cos omega by 2. This is the frequency response. Let us sketch the magnitude and the phase of this frequency response and recall that for discrete systems, it is adequate to sketch the magnitude and phase, or for that matter to determine the magnitude and phase response in the region omega going from minus pi to plus pi. We do not need to go outside that range, because after all the frequency response is periodic with a period of 2 pi. So, whatever occurs between minus pi and pi is going to be repeated around every multiple of 2 pi. So, the magnitude of this response would be mod cos omega by 2. And let us confine, as I said, to omega between pi and minus pi, whereupon cos omega by 2 turns out to be non-negative. In fact, essentially cos omega by 2 is real and greater than equal to 0 in this region. Thus, phase contribution from this term is 0. So, if you look at the overall frequency response here, namely e raised to the power minus j omega by 2 times cos omega by 2, this has no phase contribution. For minus pi less than equal to omega less than equal to plus pi, and the phase contribution comes only from here. The phase contribution from this term is going to be equal to minus omega by 2. So, now we can sketch the phase and magnitude contributions very clearly. Let us sketch the magnitude response. The magnitude, again, this is a real filter. This is a filter with a real impulse response. Now, when an impulse response is real, the frequency response is conjugate symmetric. So, whatever is at omega is also at minus omega in magnitude, whatever is at omega in phase is the negative of what is there at minus omega in phase. So, we need only sketch the magnitude response and the phase response between 0 and pi. We can ignore minus pi to 0 because there is going to be conjugate symmetry. So, let us sketch it only between 0 and pi. You can see that this is the kind of pattern that is going to show, essentially of the form cos omega by 2. And for the moment, we can already see that this is something like a crude low pass filter. I say it is a low pass filter because it emphasizes the lower frequencies and de-emphasizes the higher frequencies. I say it is crude, it is far from ideal. In fact, if you had an ideal low pass filter, then of course, you need to specify the cutoff too. So, an ideal low pass discrete time filter with a cutoff of pi by 2 would look something like this. I mean, in the magnitude sense. So, it would have a magnitude response that looks like this. And ideally, the phase response would be 0. So, it would be 1, the response itself would be 1 between 0 and pi by 2 and 0 between pi by 2 and pi, and of course, mirrored as it is between minus pi and 0. So, ideally, we would have this magnitude and phase equal to 0. Where are we in reality? We are trying to replace this ideal filter here with this crude approximation to the low pass filter here. So, please remember, this is the ideal towards which we are striving, and this is where we have reached in some sense with this very simple Haar multi-resolution analysis or Haar filter bank. Now, we shall understand this even better when we look at the magnitude response of the high pass or the other filter in the filter bank. But for the moment, let us complete our discussion by also drawing the phase response. So, the phase response of this filter is as follows. The phase response, as we noted, was minus omega by 2. So, in the region from 0 to pi, at pi it would of course take on the value of minus pi by 2, and this is a straight line. So, in fact, you get what is called linear phase. Now, linear phase is something very attractive in discrete time signal processing. In fact, one of the reasons why people go to discrete time signal processing from analog signal processing is because you can get linear phase. Why is linear phase important? Let us spend a minute in reflecting on this. You see, what does the phase response denote? Or for that matter, what does the frequency response denote? The frequency response tells us what happens to a sine wave when it passes through the system. So, in fact, to understand this better, let us go to continuous time first. Suppose we fed a sine wave, let us say cos omega naught t plus phi naught times A naught. So, amplitude A naught, frequency capital omega naught, phase phi naught, to a continuous system, to a continuous time filter. With frequency response let us say h as a function of omega, what would come out? Very simple. You would evaluate the frequency. This is of course a complex number as a function of capital omega. You would evaluate this at omega equal to omega naught. The magnitude would multiply the magnitude, the angle would add to the angle here. So, in other words, what would come out is mod h evaluated at omega naught, A naught cos omega naught t plus phi naught plus angle of h evaluated at omega naught. What is the effect of this angle? As you can see, the effect of this angle is to change the phase, and a change of phase is equivalent to a change in time. So, it is like shifting the time, shifting the sine wave on the time axis. So, angle h omega naught essentially shifts the sine wave, shifts the sinusoid by t is to be replaced by t plus something, and that plus something is given by this divided by omega. So, I mean let us write it out explicitly that way, let us reason out what it should be explicitly. So, we will rewrite that expression, we will write it as mod h omega naught times A naught cos, we will keep phi naught as it is, we will take omega naught common, and then we will write t plus the angle of h omega naught divided by omega naught. I am sorry, yeah, well I will write omega naught t plus this into omega naught. So, again you have angle here. So, this into omega naught, I will write it this way. So, now I can rewrite. So, forgetting about this part, see this part is essentially a change of magnitude, it is only this part which I wish to focus on. T has been replaced by t plus angle h omega naught by omega naught. So, essentially this quantity angle h omega naught divided by omega naught is like a time shift, is that right? It is an important observation we make. Now, just in case it is independent of omega naught, we have a good situation. So, this time shift actually is what is called a necessary evil in the frequency response. Most of the time when we give specifications for designing a filter, whether it is in the analog domain or in the discrete time domain, we do not really want a phase response. The phase response comes as a necessary evil and we have to work around it. Now, what does the phase response do? At at each frequency it creates a time shift. So, the phase response creates a time shift dependent on frequency. What is a good situation to have? An ideal situation is no phase response. This is unachievable. In fact, it is unachievable because of causality. If you want the filters to be causal, then you cannot ask for 0 phase. Incidentally, that is why you can use 0 phase filters in dealing with images, in dealing with 2-dimensional data. Because in 2-dimensional data, causality is not an important requirement. But when you are dealing with 1-dimensional data in time, causality is essential. You cannot avoid it, and therefore, you cannot avoid a phase response either. Now, if you must live with a phase response, what kind of a phase response would you like to live with? You would like to make sure the phase response does not treat different frequencies differently. So, if it has to shift a sine wave in time, so be it, but then shift all sine waves by the same time, and that is exactly what we are saying when we talk about linear phase. Linear phase means angle h omega naught by omega naught is independent of omega naught. That means it is a constant. Let us say it is some tau or tau naught if you like, which means that the angle of h omega naught is of the form some omega naught times tau naught. It is linear in tau naught, in omega naught. That is why it is called linear phase. Now, this is what I am trying to emphasize at this point. This very simple filter bank, the Haar filter bank, has this beautiful property of linear phase. By the way, this is something unusual in filter banks. It is not easy to design filter banks of larger order with linear phase. In fact, only one class of filter banks has this property. Linear phase in some sense has to be compromised with something else. So, in the Haar you can have your cake and eat it too. So, you can have linear phase, you can have orthogonality. But later we will see that if you want to get something else out of your filter bank, if your filter bank must be better in some sense, you have to sacrifice linear phase. Anyway, so far so good, we have linear phase, we are not doing badly. And if we look at the second filter in the Haar filter bank, we shall have something similar. So, let us look at the second filter, the second analysis filter. And that is of course 1 minus Z inverse into half. Let us again find out how this filter looks in the frequency domain. So, the frequency domain would show it as Z equal to e raised to power j omega, whereupon we have 1 minus e raised to power minus j omega by 2, and we play the same trick. We take e raised to power minus j omega by 2 common, and we have e raised to power j omega by 2 minus e raised to power minus j omega by 2. And once again one can recognize this is essentially 2j times sin omega by 2. So, now I can simplify this, put it all together. Once again, I look at the magnitude response first. The magnitude response is the magnitude of this, and that is easily seen to be mod sin omega by 2. Let us sketch the magnitude response as a function of omega. Again, we will sketch it only between 0 and pi for the reasons that I have just explained. So, it will have an appearance something like this. This is going to be 1 here, this is mod sin omega by 2. Now, for the phase response. Now, please remember, last time we had a convenient situation. We had two terms, one of them contributed no phase, the other one contributed a phase. So, we were comfortably put. This time we have to be a little careful. So, let us make life easy by first looking at only 0 to pi. Remember, we are going to have conjugate symmetry. So, let us consider omega from 0 to pi, and let us look at the frequency response expression j e raised to the power minus j omega by 2 times sin omega by 2. Sin omega by 2 is non-negative, so no phase contribution here. However, both of this term and this term have a phase contribution. In fact, the phase contribution is 90 degrees or pi by 2 from here and minus omega by 2 from here. So, overall the phase contribution or the phase response is, only between 0 and pi, pi by 2 minus omega by 2. This is contributing essentially j in the expression, and this part is coming from e raised to the power minus j omega by 2 in the expression. Let us sketch this response. The phase response. So, of course, at omega equal to 0, it is going to be pi by 2. And at omega equal to pi, it is going to be 0. This is the situation. Now, once again we have linear phase. Well, almost not quite linear. If it were strictly linear phase, this would have been a straight line indeed, but a straight line passing through the origin. So, it is not really linear phase, this is called pseudo linear phase, seemingly linear phase. In fact, for completeness, let us draw the magnitude and the phase response all the way from minus pi to pi for both of these filters now, for the sake of completeness. So, the situation is for the filter half 1 plus Z inverse, the overall magnitude response should look like this, between minus pi and pi, I mean. Essentially mod cos omega by 2. And the phase. This starts at plus pi by 2 here and goes up to minus pi by 2 there. Passes through the origin, of course, a straight line. For the second filter, the overall magnitude response looks like this. Essentially a sine, mod sine omega by 2. And the phase response looks like this. Starts at pi by 2 there and goes to 0, it is a straight line segment. Here it would start, now that is interesting. You know, the phase on this side between minus pi and 0 needs to be the negative of the phase between 0 and pi. So, it will be a mirror image. These are lines, straight lines. So, we call this pseudo linear phase. Now, one point needs to be understood. There is a peculiar situation at the point omega equal to 0 here. The phase is both pi by 2 and minus pi by 2. How can this be possible? Well, the answer comes from the magnitude response. The magnitude response at that point omega equal to 0 is 0. When the magnitude response is 0 at a point, the phase response has no meaning. The phase response could be anything. You see, it means that sine wave at omega equal to 0 is anyway being destroyed. So, what consequence is the phase response? That is why there is an ambiguity in phase or a discontinuity in phase at the point omega equal to 0 in this phase response. A small detail, but important when we try to understand this filter bank completely. Anyway, coming back to these magnitude responses now. If we consider the two magnitude responses together, in fact, let us first consider the frequency responses together, both magnitude and phase. A very interesting property emerges. You see, suppose we add them. So, suppose you take I do not even need to substitute z equal to e raised to the power j omega. Let me keep it as it is. So, half into 1 plus z inverse plus half into 1 minus z inverse. It is very easy to see this is equal to 1. A very interesting consequence. What does it physically mean? It physically means that if I were to send a sampled sine wave of frequency omega into one of these filters and then the other, and if I took these two sampled sine waves from the two filters and put them together by adding, you would get back the original sine wave. So, sine wave at frequency omega is split by these two filters in such a way that the parts can simply come together and reconstruct the sine wave as it is. Now, let us look at something more interesting. What can we say about the power? So, recall that if you give a sampled sine wave, a sampled sinusoid to a discrete time filter, let us say the angular frequency is omega and the frequency response here is h of omega. Then the power that emerges from here is proportional to mod h omega squared. So, in other words, whatever is the power of the sampled sinusoid with angular frequency equal to omega here is multiplied by mod h omega squared when it emerges at the output. So, the squared magnitude of a frequency response is indicative of the change in power of the sine wave when it goes through that discrete time filter. What can we say about the power change of a sine wave when it goes through either of these two filters here? Let us see. So, that means in other words we are asking the question, what is the magnitude squared response in the first one? It is mod cos omega by 2 the whole squared, and in the second one it is mod sin omega by 2 the whole squared, and lo and behold, when you add these you get 1 as well. That is a very, very interesting observation. Not only does it happen that when you add the two responses together, you literally took 1 plus Z inverse by 2 and 1 minus Z inverse by 2, the actual frequency response is irrespective of Z. In fact, I said there you did not even need to substitute Z equal to e raised to the power j omega. You just added the system functions together and you got 1. So, if you put a sine wave of frequency omega, I mean a sample sinusoid of frequency, angular frequency omega, and looked at the corresponding emerging sine wave on the top branch and the lower branch and just added them together, you would get back the original sine wave. Not only that, what we have just shown is that when you multiply, if you look at the power emerging from the upper branch and the power emerging from the lower branch, the powers also add. So, in fact, you have two kinds of complementarity in the filters. This is something very, very interesting here. So, if you call the frequency responses of the upper branch and lower branch respectively as H upper omega and H lower omega. Upper branch, lower branch. Then two properties are immediately satisfied. H upper omega plus H lower omega is equal to 1. This is called magnitude complementary property. And in addition, mod H upper omega squared plus mod H lower omega squared is identically equal to 1. This is called the power complementary property. A very interesting result. The Haar analysis filter bank is both magnitude complementary and power complementary. In fact, I leave it to you to study the synthesis filter bank and come to a similar conclusion. The filters are magnitude complementary and power complementary. Whatever it be, this is something striking. Now, you see what I mean when I said the filters have individual properties and collective properties. Magnitude complementarity and power complementarity are collective properties. The low pass and the high pass nature, if you recall, the second filter that we had was high pass, because it emphasized higher frequencies and de-emphasized lower frequencies. So, the low pass and high pass properties are individual properties. The magnitude and the power complementary properties are collective properties. So, we have filters with individual and collective properties forming two filter banks, the analysis filter bank and the synthesis filter bank. Now, the idea of a filter bank is very deeply entrenched in multi-resolution analysis. In subsequent lectures, we shall study this connection even further. So, for today, we shall conclude the lecture here by noting that we have already established even more deeply the frequency domain behavior of the filter bank that we brought out in the previous lecture. Thank you.